Hi everyone. In this video, we will continue this discussion of rational-like functions that we had before, and we will generalize. Here's a generalization for rational functions, which you have seen before. Right? So you have, if a function is a rational function, it's of the form p over q, where p and q are polynomials, which means p is something like a n x to the n, and minus 1 x to the n minus 1, blah blah blah, a naught, and qx is some other polynomial with some other degree, like say m. Now if n equals m, that is degree of p equals degree of q, then the limit as x goes to plus minus infinity of this rational function is an over bm. Okay, which you have seen before as saying that these are the ratio of the leading terms of both of them. And this becomes obvious when you think of our method. What would we do in this case is we would divide both sides by the highest power. But if the highest power is the same, then the first terms are just going to be numbers, and then the limit is just the ratio. So y equals this ratio is a horizontal asymptote. If n is more than m, that is, the degree of p is greater than the degree of q, then this limit is plus or minus infinity, and there are no horizontal asymptotes. Okay, again, why is that true? Because if the degree of the numerator is more, when you divide, everything in the denominator becomes 0, right? Becomes closer and closer to 0, which means it's going to be some number divided by something really small, which goes to infinity. Or another way to think about it is if the numerator has a larger power, it's much bigger than the denominator, so it goes to infinity. If the opposite scenario happens, then we have something called a slant asymptote. And how do we find that? We're going to look at it on Thursday. Find it using division of polynomials. Okay, for example, if I have a function x cubed plus 1 over x squared minus 1, then this has no horizontal asymptotes. Okay, because this function this is not correct. If the degree of p is more than degree of q, then we have the case before. Oh, I think I lost the thing that I cut. Delete. Okay. Then we find using the division of polynomial. If n is less than n, right, then you always have that this limit is going to be 0. So y equals 0 is always a horizontal asymptote. This is only in the case of rational functions. So if this happens, there's going to be a slant asymptote. If you have the other way around, then as x gets larger, the denominator gets much larger. So y equals 0 is a horizontal asymptote in this case. Okay, now let's look at some other examples, some other tricks, examples. Now one of them is, suppose you have to find this limit, square root of x squared plus 1 minus x. Okay, now we make a few observations. First of all, there are no fractions. Secondly, it's a square root of an x squared thing, which is about x. And the last thing is, whenever you see a square root minus some stuff, you're always wanting to think of some sort of rationalization. Okay, so you can think of this as that fraction, and we try to rationalize the numerator. That is really the only thing we can do here, and that is the most common trick we have for these kind of situations, whenever there is a square root stuff going on. So I multiply by the conjugate, which is square root of x squared plus 1 plus x. But to keep things balanced, I have to do that on the denominator as well. Now on the numerator, since this is a difference of squares, it just becomes x squared plus 1 minus x squared, and I have x squared plus 1 plus x, which then becomes 1 over square root of x squared plus 1 plus x. Now here, this is much larger than 1. So this is 1 over some large number, which is going to be 0. Or you can divide by x to get limit x going to infinity 1 over x squared over x squared plus 1 over x squared plus x over x. So you can already see that since the numerator is going to be 0, and the denominator is non-zero, this is going to be 0. So in this case, you have a large number and you subtract another large number and you end up with 0. But that is not always going to be the case. Another example is limit x going to infinity of sine x. What is this? We say this does not exist because the function oscillates. Okay, so if you look at the sine function, and if you look at it in any direction, you cannot pinpoint a certain value that it will settle onto. So you cannot say that the limit exists. And remember, whenever we don't have a clear-cut answer about what the limit should be, then we don't say what the limit is. We say that the limit does not exist. Here's a cautionary example. Limit x going to infinity of x cubed minus x. Okay, now if I say that this is limit x going to infinity of x cubed minus limit x going to infinity of x, which is infinity minus infinity, is 0, this is wrong. Because anything going to infinity minus anything going to infinity may or may not be 0. It's not always true that it will be 0. Okay, this is something that you will see in more details in Calc 2, where these are called indeterminate forms, and then we have other techniques for drawing conclusions. But here is the correct way to draw a conclusion is to factor. If I factor, this is x times x squared minus 1, and by limit laws, this is going to be, so if you have something going to infinity and you multiply by something going to infinity, then it definitely goes to infinity. Okay, so the limit is infinity. If you have something that goes to infinity and you multiply by something that goes to infinity, then it will go to infinity. If you have something going to infinity multiplied by something going to negative infinity, it will go to negative infinity. However, if you have a subtraction of two things going to infinity, then they will necessarily not go to 0. They may go to some other number. They may go to infinity, they may go to 0, they may go to any number. So those kind of conclusions cannot be drawn cannot be drawn that easily. So we have to be a little more careful about it. So these were some of the things that I wanted to go over on Tuesday. And just have some examples here. You can go ahead and try some of the worksheet problems, which ask you to find limits at infinity. And on Thursday, we will be meeting not in person, but over Zoom, and I will go over the idea of curve sketching, which is going to use this finding horizontal asymptote. So in there, we're going to put everything together. Yeah? So these are some things that you should review before Thursday's class. We will be using finding domains, intercepts, symmetry, which is odd even function, even function, asymptotes that we looked at today, horizontal and vertical, increasing, decreasing intervals, how to find that using calculus, local min, local max, how to find that using calculus, concave up or down, and inflection points. So these are sort of things that we talked about today, plus your pre-calc ideas, and these are the ideas that we have learned in calc so far, and we will be using these together to plot graphs of any function. Okay, which means at that point, now any function that you're given, you will be able to draw an approximate graph of what it looks like by combining these sort of 8 pieces of information. And that's going to be our goal on Thursday. I'll just do, so make sure you look at the definitions of these things and are comfortable finding them. I'll do a few examples, and then we will go into the Jamboard and break into groups and work on some problems. That's it. Thank you, everybody.